Okay, so how many are here? 33. All right, so let's start. So we have kind of finished with the first module, if you want to call that, which was about some basic graph traversal algorithms, including BFS, DFS, and finding mm, the ordering and so on, topological ordering in directed graphs and so on, and some like application of BFS, like finding bipartiteness in a graph. Okay, so today we will move on to another topic, which is going to be about greedy algorithms. So, I mean, if you go through the book tries to give a sort of introduction that, okay, like, in this movie called Wall Street, there was this line, greed is good, and is like, can we exploit or can we use such a maxim or such a policy in some kind of algorithms and that can be useful for us, or we can find some nice results using that policy. So what does it mean for an algorithm to be greedy? So first thing is that, like, there is no, like, one very technical definition. This is a class of algorithm which is which we call greedy, and it's not like when we define it, it's not that it's a very precise definition and it can be applied to very clearly to any algorithm, because there are so many algorithms and so on. So there might be some algorithms which there can be a debate, which are greedy or not, but there are some, like, basic things which, if you see, then you can say that something is greedy. So one thing is that it builds the solution in small steps. So it's not that it will keep doing something and in the end the solution will come up due to, like, some other structure. In each step, or in small steps, it will be making some part of the solution. Okay, and at each step the algorithm will make some myopic choice. And what do you mean by myopic? Right? Depending upon some criteria. Okay, so again, this is a very loose definition, but we'll see what does it mean and what do we mean by, like, myopic. So that the algorithm does not really look ahead, or does not really, so whatever it knows till now, it will, so it is, like, short-sighted in that sense, and that's what the synonym of myopic. And it just looks at what it knows till now and makes the decision on the basis of that, and then it will apply some criteria to the existing things which are there. Okay, so this is just like in a very rough way, to look at, like, what are greedy algorithms and so on. Okay, and also, so why would such a thing work? That is a another question. That you have a huge problem, and each step you are being greedy. Why would that work for the whole problem? Why would that produce the optimum solution for the whole problem? And that is where the hard part of the algorithm is there, that proving the correctness can be tricky. because the algorithm is going to be simple. Why? Because in each step it is just going to evaluate some criteria, and on the basis of that it's going to decide. But if it works, it usually tells or about some structure of the problem. So not all the problems, for not all problems, this kind of algorithm works. The greedy algorithm works. So we whenever we are able to design that, then it tells something nice about the problem, and that might be so if you want to that is not in the scope of this course actually, but there is this nice mathematical structure which lies beneath the problem if a greedy algorithm works on that, and that is called matroid. So if a greedy algorithm works on a problem, then it has to have an underlying matroid structure. And if a problem has an underlying matroid structure, then greedy algorithm will work. So this is actually a characterization. So it's a very mathematical object, matroids, and then but yeah. So, but we will not be getting into that. But let's just keep in mind that some very nice properties of the problem, get revealed if a greedy algorithm is shown to work on that problem. Okay. So there are two basic ways. So in which we'll prove proving the correctness. First one is staying ahead method. And second one is exchange argument. So what is staying ahead? That the algorithm stays ahead of any other algorithm at each step. Ahead at each step of any other algorithm. So what does this mean? That whatever algorithm is there, any other algorithm, this algorithm is doing better at every step, and hence at the end also it is doing better. Again, we'll look at these things with examples, and then it will be more clear that what do we mean. And exchange argument, given any solution through exchanges, we can reach the solution output by the algorithm without making it worse. So you are like, okay, give me any solution and I can reach the solution of the algorithm by changing it. And in each step, I'm exchanging some part of the solution. But in each step, I'm ensuring that I'm not making it worse. So if I reach the full solution, then it is not worse than any other solution. So any other solution is at most as good as this solution. So I mean, yeah, this thing just again, we'll see this with examples and it will be more clear. So since I'm saying about examples, let's just look at one example, which is a very popular problem. It's called interval scheduling. Okay. So input is n time intervals. Okay. And let's say they are represented by the set 1 to n. Okay. And each of them have a start time. SI and finish time. TI. Okay. And we say that two intervals are compatible if they don't intersect. Like so, I mean, all right. So what is the output that we want? Largest set of compatible intervals. So suppose, so let's just like, so is the problem clear? Okay, let's make it clear even more. So suppose this is your number line, whatever. And then intervals come like this. So one interval is like this, another interval is like this, another is like this, like this, like this, something like all this. It's like this also. So intervals come like this, and from all these, and maybe something can be very long, something can be very short, something can be longer. Okay, so the first one is the start time. So suppose this is the time increasing. So this is, if this is interval I, this is S of I, start time, and this is F of I, the finish time. Okay, and what do we want? We want the largest set of disjoint intervals, compatible intervals. Okay, so here in this case, let's say, I mean, we can at least schedule 3. Yeah. So suppose this one was in the middle somewhere instead of here. Here, so if this one was here, it was a very short interval here. Then you can actually schedule these 4. Right? So the question is that once you are given this interval, not always it will look so nice like this that you can see these things. And then how do you find this disjoint sets of interval of maximum size? Okay. So this is what the problem is. So suppose we want to design a greedy algorithm for the problem. So let's just, for the sake of, understanding and, for exploration, let's look at, first some wrong approaches. But like, what will the approaches do? Any of the greedy algorithm, as I said, that small steps, and at each step, make a choice. So here, what is going to be the choice? Include some interval to the solution. And then this make a choice will be based on some criteria. And this is the criteria that we will be, that will differentiate different set of algorithms. Okay. So let's just look at, as I said, some criteria. Okay. And see how do they work. So one person can think that, okay, however the algorithm comes, let's just schedule the first algorithm, the algorithm that starts the first. Okay. So at each step, choose the interval, I kept saying algorithm. Choose the interval or request that starts first. So basically, you choose this one and then you delete this from the set, and then in the next step you see, okay, whatever starts first, this maybe or whatever. So and then you choose that, and then next step you choose that, and so on. So is this correct? Is this correct?
No, sir.
Why?
Small intervals may be missed.
Small
I mean,
intervals.
I mean, I mean,
Okay.
like you start uh, means for the whole time interval. First, the smallest time is means we can give
Okay.
a counter example. We can that
Okay,
okay.
sure. So we can give a counter example, but yes, I would also like to do what you were trying to do. That we also try to see that what is the property because of which this is wrong, or just try to understand in our own terms, in our own words. That okay. So okay, what can be a counter example? So this is our line. So how will the intervals look like in which will be the counter example? Rishi?
Two intervals that lie within this interval and starts after this
Okay. Yeah.
interval
So suppose
starts.
this itself is an interval, and this is your number line, whatever. So yeah, and then there are two intervals which lie and they are disjoint, right? And they start after, right? This is what you're saying, Rishi.
Yes,
Yeah. So now the thing is that this interval, even though it starts the first, so it will get scheduled, but this is so long that this cannot be scheduled and this also cannot be scheduled. While so the algorithm outputs one or serves one request, while optimum is two, right? So the idea is that the starting algorithm can be very long, and that might kill the possibility of scheduling many other algorithms. Many other, again, I keep saying algorithms. The starting interval might be very long, and that might kill the possibility of scheduling other intervals or other requests. So initial requests can be very long. Okay, good. So this, I mean, this problem is very common, right? That okay, you have many jobs on an operating system. You want to schedule as many of them as possible, and so on. So I'm not getting into applications too much because like, yeah, that you can figure out. Attempt to. Okay, good. So suppose now we want to make another attempt, and as like Rishi was saying that okay, maybe smallest or something. So what if we choose the smallest and include the smallest in the solution recursively? So what is it doing? It finds the smallest one. Okay, so others are long, others are long. Then it finds the smallest one and then it includes in the solution. Actually, I had made like yeah, and then deletes all the ones which are not compatible with that, and then finds the smallest and so on. So this works for this particular example here in the first one, but is this correct?
No, sir.
Why?
Sir, because a small time interval can be in the intersection of two other time intervals.
Exactly. So you have these huge intervals, and there is the small interval, okay, which is so here. This is the counterexample, right? And again, this counterexample works for the previous, just like the previous case. All right. So this intersection is causing the problem. So let's do attempt 3. And attempt 3 says that find the interval with minimum number of conflicts and schedule that or include that. So again, include that in the solution. You include that in the solution and delete all the intervals which are not compatible from the set and so on. So is this correct? Any guesses?
We can have exactly the same start time and finish time of one interval, and like lots of interval with the same start time and finish time. So that would lead to lots of conflicts, but it still may be a valid choice.
Exactly. So as Javneet said, so that there can be many intervals which have like same start time and same finish time, but still it is the more optimum solution because you are able to so okay, so let's do it. But still it is not so easy to design. I mean, so this idea remains the same, what Japneet said, but designing a counterexample in this case is not that trivial also. But let's try to do this. Okay, so there are many intervals here. There's one in the middle. So this is an example in the book. You can have a look at that as well. And then there is this one. So this is intersecting here. And this is intersecting here. And this is intersecting here. And this is intersecting here. Okay. So if you want to remove the least conflicting one, then you will include this. And then you are stuck because then you can never have this 4 guys scheduled because you cannot schedule these 2. Right? So optimum is 4. And the algorithm outputs 3. So any questions till now? So the algorithm actually includes this one because this has only 2 intersections. Every other interval has like 4 intersections. So then it will include this, but since you include this, you cannot include this, you cannot include this. And now out of these 4, only one can be included. Out of these 4, only one can be included because they all intersect. Okay. Okay, so let's make another attempt. So we started with smallest, like, whatever started the first and so on. But let's say include in the solution the request that finishes first. Okay. So here, this will include this one first. Then, okay, these cannot be included anymore. So they will get deleted. Then it will include this one. Then this cannot be included. Then it will include this one because this finishes first among the remaining, cannot be included. Then it will include this one. So it will work for the previous example. But is this correct?
Yes, sir.
Okay, why?
So we can start with an optimal solution and then like we can use that exchange property from the leftmost interval.
Say again, we can?
We can start with an optimal solution
Yes.
and we can use that exchange property and show that if we apply this greedy property, then it is not worse.
Yeah. So actually, we'll not be doing it by the exchange property argument. We'll be doing that it always the first one, which says that it always stays ahead. So we don't, yeah. So we'll be later looking at the exchange one. So this is actually so, but again, so what you see is that first it is not very obvious that why it should work, or why it is the optimal one, because even these ones, if you see, the criteria is very similar to the other criteria. In some you were looking at the start time, in some you were looking at the intersection. Now we are looking at the finish time. Why this has to be better prima facie, right? It is not. I mean, it is not if you just look at it by. So you need to show that why this happens, or why this is actually gives an optimal solution. So, as Anshuman was saying, we'll be looking at how to do that. But before that, let's make it slightly more concrete, the algorithm, so that it will be easier for us to, show the correctness. So the algorithm maintains two lists. Set R of, or remaining requests, let's say. And A of accepted requests. So now I'm using the term requests. So these are just intervals, So requests, why we use is from some operating system applications and so on, that these requests have come to the operating system and it wants to schedule. So that's why interval scheduling. So the requests have some interval when they want to be scheduled, and the operating system wants to maximize the number of intervals or the number of requests that it can serve. Okay. All right. So these two sets will be maintained, and the algorithm is simple. While R is not empty, so it will do what? Choose a request I belongs to R with smallest finishing time. Okay. Add I to A. Delete I and all incompatible requests with it from R, and that's it. Now you end the while loop, and then when R becomes empty, then you just output the solution. Is accepted requests. Good. So this is the algorithm. It is not like, what we said. We have just written it down in slightly more precisely that, okay, we start with R is equal to full all set of 1 to n, let's say. Initially R is the whole set. So we start with the whole set, then we look at, okay, which one has the smallest finish time. Then we add that to the solution, and then we delete all the, since we have scheduled it now, or since we have included it in the solution, now any of the incompatible ones cannot be in the solution. So we delete those. So we delete that I and all the incompatible requests from R. And then, okay, then again, we have to look for the next, request that finishes first. Is the algorithm clear? Any questions about the algorithm? No? Okay, good. So let's prove the correctness. And that's where we'll be using this, the first way that we saw that the algorithm stays ahead. Okay, good. So first, let's just get this out of the way that the output is a set of compatible requests. Why this is the case?
Because at every step we are deleting all the incompatible requests, so no such request can ever enter the set A.
Exactly. So this is just due to due to step 4 of algorithm, where we delete like whatever the set of incompatible things. So this was just a sanity check that okay, whatever we are outputting, it's actually set of compatibles. All right, but now we want to show that the algorithm actually outputs an optimal solution. Okay, so that's where now the staying ahead thing will come. Let's see what we mean by that. Okay, so let's look at some optimal solution. O, okay, which is a subset of, so sometimes, okay, I'll also use for 1 to n, I'll use this notation. Okay, so this is how you write definitions, but okay. So suppose there is some optimum solution O, which is a subset of n. So what do we want to show? Can we show that the algorithm outputs O? Can we show such a thing? I mean, ideally we would want to show that, but can we show such a thing?
There might be some other optimal with the same number of tasks.
Exactly. So that might not be true. Because there can be many optimums. With same size, right? I mean, this part is actually redundant because they are optimal solutions, so they have the same size, but still just to emphasize. Okay, good. So what would we want? So we would want to show that if there is an optimum O, then we want to show that whatever we are outputting is not worse than O. That suppose we output the set A, then the size of A is greater than or equal to the size of O. Right? And that actually means that size of A is equal to size of O. Why? Because O is already an optimum, so you cannot, get something larger than O anyway, right? Is that clear? That what we want to show? Okay, good. So now let's just make it slightly more precise, and let's look at what are the intervals, which are there. So let A is equal to, so let's say A has k elements, so I1, I2 to Ik, and let O has m elements, so J1, J2, Jm. Okay, and we want to show that k is equal to m, right? And let's just like, for our this thing. So let's assume that both A and O are ordered by finish time. And hence start time also. So what does this mean? That I1 is the interval in A which finishes first. I2 is the interval in A that finishes like, first after I1 and so on. Similarly, J1 is the interval in O that finishes first. J2 is the interval in O that finishes after J1 and so on. And why do I say that? And hence by start time also, the ordering will be the same.
Because
they are
like
incompatible.
Yeah, because they are compatible, because none of them intersect, right? So if none of them intersect, then like, you can show that if the start times are ordered in some way, then the finish time will also be ordered in the same way. Or if the like, finish time is ordered in some way, then the start time will also be ordered in the same way. Like, it's an if and only if. Okay, good. So there's one thing that we definitely know, that initially the algorithm looks at all the jobs and selects the one that finishes first, right? So we know that I1 is less than f of I1 is less than or equal to f of J1, right? That we know because of the first step of the algorithm. Choose a request I in R with smallest fi. So so this I1 has to be the smallest fi of all the jobs. So J1's fi cannot be less than strictly less than like finish time of I1. J1's finish time cannot be strictly less than. So this is what the lemma actually we would want to show, that this is actually true for every thing in the set. So for every r less than or equal to k, let's say f of I r is less than or equal to f of j r, right? And how can we prove this? How can we prove this?
Induction.
Yep. So proof is by induction, and we have already seen that so this is due to the step 2 of algorithm, I guess, if I'm not missing something. Okay. So by induction and the base case we have already seen. And now suppose for induction step. So we know that f of I r is less than or equal to f of j r. And now we want to show that f of I r plus 1 is less than or equal to f of j r plus 1. Okay, so let's just look at it pictorially and it will become very clear. So suppose this is your line and this is, okay, let me use different colors so that it is more clear. So suppose here was your IR and here was your IR plus 1. Okay. Now can JR be something like this?
No,
Why?
because the finish time is before.
Yeah, so the finish time of JR cannot be before the finish time of IR, right? So it has to go further. All right. So now, since JR plus 1 is ordered after JR, can it intersect with IR? No, right? So if anything, it can only start after JR, So it cannot intersect with IR. Right? So JR plus 1. So what does that mean? That IR and JR plus 1, they are compatible. So what does that also mean? That when IR was included, JR plus 1 was not deleted from R. Right? That means that JR plus 1 is still available. For the next iteration. Now, suppose for the sake of contradiction, that f of JR was strictly less than finish time of IR plus 1. Then why does this give a contradiction?
Sir, you mean JR
Because our
plus
algorithm can choose JR.
Oh yes, JR plus 1. You are right. Yeah, sorry.
Because
So somebody.
then our algorithm will choose JR plus 1 instead of IR plus 1.
Exactly. Then the algorithm will choose JR plus 1 instead of IR plus 1, which is a contradiction in next iteration. So this is the contradiction. So we have that f of JR plus 1 is greater than or equal to f of IR plus 1, which is what we wanted to show for the induction step. So finishes the induction step and finishes the proof. All right. So this is what we wanted to show. So this is what that each step, the algorithm is doing, like, the best, like, that is possible. That you take any optimum. In fact, forget about any algorithm. You take any optimum set, and the algorithm is doing better than that at every step. So why this is better, or why does it actually imply an optimum solution? So let's look at that with another lemma. So let O be then what we want to show is A is greater than O, at least O. Okay, so let's write it and test. And how do we show this using the previous lemma? So okay, let's make it again slightly more precise. Just a moment. So let's say A is equal to I1 to IK and O is equal to J1 to JM. I think that's what. And we want to show that K is equal to M. Yeah, or greater than equal to M. Yes.
So at any stage R, like at any stage I, the remaining set R from our algorithm is a superset of the one which will obtain from the O while making O, because like the end time in our algorithm is earlier than the end time in O, so the number of remaining intervals are more. So obviously our solution would be better eventually.
Yes, but how do we show that the whatever is left is more?
Sir, because like we are deleting all the intervals which are overlapping, right? So if the at ith stage our finish time is before the one from O, so we'll obviously be left with more intervals ahead, right?
Exactly. So I mean that is correct. So just to be more precise, or
So,
at least one way of we
could say this for the last stage as well. So at the stage K, we'll be left with intervals.
Yeah, what we know from the last lemma that ik, f of ik is less than or equal to f of jk, right? So if m is less than k, then there are some interval left. Then look at, like, let's say, look at j k plus 1. Okay, if m is less than k, I should say, or if m is more than, if m is greater than k. Okay, then look at the jk plus 1, right? So now jk plus 1, just by previous logic, is compatible with ik. Yeah, Shravan. Do you have another question?
No, sir, no.
Okay. So so jk plus 1 is compatible with I1, so was not deleted when ik was selected. So that means R is not empty. So the algorithm will not stop. And select at least one more. And what does that mean? That mod A is greater than K, which is a contradiction. So basically what are we saying? That, okay, the algorithm was doing best at every stage. So look at, like, you know, the kth step. And if suppose this was JK, suppose this was JK actually, and then we had more JK plus 1 and so on. Then look at here. We know that IK finishes before JK, and again the same logic that, okay, this is IK, this finishes before JK. So now if there is JK plus 1, that is later. So it is compatible with IK, and that is why that JK plus 1 will be available for the algorithm for the next choice, and that is why it will not just stop at K, it will get something more. Right? So that is why this algorithm computes the optimum. Any questions about the proof? Okay, no. Okay, so let's quickly do the running time analysis of algorithm, or how to implement this. So first thing is just, you know, make two lists, or just sort according to finish time. Okay, so let's let the list be again I1 to IN be the list. And you also have corresponding numbers and their lists, like, you know, F of I1 to F of IN. Let's call this list whatever, big F. Then you have S of I1 to S of IN. This is the, let's call this list S. And so this one is sorted, of course, in increasing order. This one might not be sorted because you got the I1 to IN by sorting the finish times. And now what will the algorithm do? It will include the first FI. So how much time will the sorting take? Order n log n, right? Now it will include the first in the list, first interval in the list F. Okay. So it will include that. Then scan in the S list from left. Start scanning. Okay, so is this one? So you got to the first one. So this is suppose the first interval. So this was I1. Okay. Now this is F of I1. Now look at the start time of all the, so now there are many other intervals. Okay, so suppose this interval, that interval, so on. Okay, so now what you want to do, you still want to scan in order of the list is already, that is in order of finish time, and you want to select that one which does not have any conflicts with the correct one, current one, right? This one goes slightly further. So which one will be first? So let's say this is 1, 2, 3, 4. So what is going to be the list? What will be the order in the list?
1, 2.
No. In this list, the list that we have made, what is the order?
1, 3, 2, 4.
1, 3, 2, 4. Right? Okay. So what did the algorithm do? It selected 1 first. Okay. Now it looks at the next one, which is 3. Is 3 compatible with 1? No, because it's start time. So it will look at its start time. So look at the next j in the list, such that start time of j is greater than or equal to, or strictly greater than, just assuming that all of them are distinct, is finish time of whatever we have selected, if I was selected. Okay, so it looks at 3 start time, is it greater than f of I? No, so 3 is not selected, so forget about 3. Then look at 2 is the next one. 2 start time is greater than the finish time of what we have selected? Yes, so select 2. So then 2 gets selected. Then now we look at 4. Is start time of 4 better than greater than finish time of 2? No. So 4 does not get selected. We finish the list, and what we are left with 1 and 2, right? So we include these guys in the solution, and we make basically one pass of the whole list. Right? So this takes order n time. So total time is order n log n. Okay. So any question about the running time analysis? Or how we implement it actually, the algorithm? There's one subtle point though, that this implementation is slightly different from what we had designed the algorithm to be, or the way we had written the algorithm. How?
We are not deleting all the incompatible edges intervals.
Exactly. So we are not deleting all the incompatible intervals, because there can be an incompatible interval which is like here, but it will come much later. So maybe there are some intervals. So now this 2 got selected, and this was not even considered, right? So then, I mean, just to prove this correctness, you need to show that this is actually equivalent to, or the solution is actually equivalent to what the earlier algorithm would output, or is the same as what the earlier algorithm would output. And that is an interesting exercise, or I mean, it's not very hard. It's actually very easy, but it is good for you if you look at that carefully.
I mean, that big line will eventually be deleted, right? Because like the start time is before the end time anyways. So
yes. So whenever
eventually it will get deleted.
Eventually it will get deleted. So yeah, this is what you have to show, that eventually it will get deleted. So like you have to be slightly more precise that okay, when it will get deleted and so on. Okay. So right now it did not get deleted.
Sir, when we are deleting incompatible incompatible element, we are repeating for while loop na. So
No, we are not. So here what we did not repeat the full while loop, because that will give us n square. That is the subtlety that I want you to think about. That if for each interval, if we choose an fi and now we want to go through the whole thing and delete all the incompatible ones. Maybe, we'll end up spending n time for each of the interval. So that might be, slightly worse. That might be n square. So that is why we have to be slightly clever and, go through it in one pass, rather than, okay, for this interval, I choose whatever is incompatible. Then for the second interval, I select whatever is incompatible, and so on. So that is, that will be worse than what we implemented. So this is slightly clever, but then this is not exactly what we had shown the correctness for. So that is why we will need to show the correctness of this also.
So we just have to show that we are not deleting the elements, but the algorithm gives the same answer.
Exactly.
I did not get your argument earlier that why are we only seeing the red top red line? We can say the same argument for lines 3 and 4 also, that they're not getting deleted, they're just being ignored.
No. So, okay, fine. If you don't want to say that. So what I'm saying is that initially they are being ignored here while one was being considered. Okay. So after one was considered, I look at some of the intervals. So I had this criteria that for whatever Sj, such that its, start time is less than this finish time of I, then we ignore it. We don't actually output it. So once it gets ignored, then it cannot be output by the algorithm. That is fine. But the thing is, because algorithm is just making the pass in this direction, but this one is not yet ignored, the red one, and it does not get ignored for this particular I, which is 1, right? So we need to just make an argument that this will not be output by the algorithm if we want to show the show the equivalence of this algorithm and the previous algorithm. So that is the difference, that for this particular I, these two were considered. And then, but this red one was not considered because there was some other thing that we found which was compatible and which had finishing time less than the red one.
Oh, okay. So we can say that the finish time, last finish time always increases. So this will never be considered because start time will always be less than the current finish time.
Yes, something like that. Yeah, that for any of the intervals later or something. So you have to do some such argument that you need to make. That's all I'm saying, that it requires a line or two of argument.
Sir, I don't understand that when we see the vertex 1 and remove all incompatible edges, then we find a new list. Suppose
Not
1, 2, and some other.
No,
Yes,
we are
sir.
not removing all incompatible edges. That
So, sir,
is the thing. Yes.
sir, what are
So
we
we are
actually doing?
Yeah. So we are just looking at this list that we have compiled, this I1 to IN, and we go from left to right in this list. Okay. So we had this list 1, 2, 3, 4, and suppose this was another one, 5. Okay. So let's say this one was 5. So we have another list that is there is another element which is 5 in there. So why now we included 1 in the solution, and now we come that okay, next finish time is 3. So 3 is not compatible with 1, so we ignore 3, right? But now 4 did not get deleted immediately. Even 4 did not get deleted immediately, even though it is incompatible with 1. 4 will still be considered. So first 2 will be considered. And then for 2, 4 will be deleted because it is incompatible with 2.
Okay, sir, I understand. We are going in a one pass and we are
Exactly.
deleting. Yes, okay, sir.
Any other question? So 5 will be deleted last because it is incompatible with 2, or it will be ignored. Okay, any other question? So yeah, I mean, this is a subtlety that, you would like, this is not there in the book also, they don't mention it, but like, this you should think for yourself that, okay, whatever we are doing, is it actually being faithful to the algorithm for which we have proved the correctness, or is it slightly different? If it is slightly different, then how do we know that this is still showing the correct thing, or this is still outputting the correct thing, and so on. So if you think about these things, your concepts will get clear more. Okay, so we are out of time. Any quick questions? Okay, if not, then thank you for coming and see you on Thursday. Thank you.